I think I am recording now. So, okay, let's start. Good morning, Professor. I am Enrique Lugo, and today I am excited to take you on a journey through my thesis proposal, which is focused on advanced nanomaterials and to develop a piezoelectric prototype. As I'm in first semester of the Master of Science in Nanotechnology, this in the future will be to obtain this degree. And my advisor here present is Dr. Nicolas Antonio Ulloa Castillo. So let's get started. The following is the outline of my presentation. First, I will tell a brief context on piezoelectric materials, and then arrive to the motivation and problem statement, also by traveling through my research question. Then later, that'll lead us to the solution overview, also the main contribution, and lastly, the dissertation organization. So let's begin with a little bit of history and to set the context. So in 1880, the Curie siblings made a groundbreaking discovery, identifying the direct and converse piezoelectric effect in quartz. This effect involve the generation of an electric charge and geometric deformation, laying the foundation for the evolution of these piezoelectric materials. In essence, the piezoelectric effect describes the phenomenon where applying pressure to a piezoelectric material generates voltage and vice versa. So, like I'm saying, it's a two-way street. So let's visualize this effect in figure number 2. As we observed in this animation, the application of pressure in this material causes microscopically a redistribution of charges, which generates measurable voltage, and this defines the piezoelectric effect. Fast forward through the years, and quartz has become one of the most renowned and extensively utilized piezoelectric materials. Other polycrystalline piezoelectric ceramics were also discovered. One notable finding during the era of World War II was barium titanate, which was mainly employed as a dielectric material for capacitors during this war. Also in 1947, Roberts made a significant breakthrough, realizing that barium titanate ceramics, particularly in the polycrystalline form, exhibited a remarkably strong piezoelectric property, which was around 100 times more potent piezoelectric properties than quartz. And also a thing to point out here is that these properties became evident after the ceramics were polarized using high voltage treatment. And in figure 1, we can also observe this. We can call it, and now, well, it's known that we can call them as perovskite structures. I will tell later why it's important. So let's continue with this context. Moving into the 1950s, the piezoelectric property of lead zirconium titanate was found to be twice as strong as the barium titanate one, and it also had a higher Curie temperature at around 300 degrees Celsius. These lead zirconium titanate solid solutions, as they call them, or PZT, as I also have it there, with their remarkable properties, they continue to dominate piezoelectric applications and obviously the piezoelectric industry. But let's remember that I was mentioning something about the crystal structure of this kind of piezoelectric materials. This is a relevant structural characteristic is that their crystal structure is non-center symmetric, which allows us to, uh, uh, when we deform this type of materials, we polarize them. As I was mentioning earlier, we deform them, applying pressure, and we could measure a voltage in these materials. However, the environmental risks associated with lead content in PZT ceramics underscore the urgency of transitioning towards more sustainable alternatives. And not only sustainable, but lead is toxic. It's found to be toxic. But let's remark some of the PZT properties. Um, while barium titanate is lead-free and was discovered prior to PZT, the dominance of PZT stem from several key advantages, which I have in here, which are adjustable piezoelectric properties. As I mentioned earlier, the Curie temperature, which above this temperature, it loses its piezoelectric properties, and low sintering temperatures, which can lead to energy savings, reduced processing time, and improve material properties, compatibility with a wider range of substrates, etc. However, not only environmental concerns necessitate exploring sustainable alternatives, but it also has been found by Lee that the manufacture, handling, and disposal of PZT ceramics present significant risk to workers and the integrity of soil and water supplies because they are having, well, these ceramics has lead. This leads us to first taste of what this research is focused on, where it endeavors to explore lead-free alternatives, such as a nanocomposite of polyvinylidene fluoride, which is also known as PVDF, and barium titanate. So these are as viable replacements for lead-containing PZT sort of ceramics, which currently dominate the piezoelectric markets. It leads us to our research question, which is maybe short, but we will obviously delve longer, deeper into it, and we could also discuss it. But mainly, the research question reads: how can lead-free perovskite-based piezoelectric nanocomposites of PVDF and barium titanate be effectively designed and fabricated for energy harvesting and integration into flexible electronics? I know maybe the word effectively might sound, well, how to measure effectively, etc. But the thing here, the challenge here is to obtain piezoelectric nanocomposites and trying to activate all the most or the larger the phases, the piezoelectric phases or electroactive phases, which are the ones that are important to this kind of application. So obviously, the aim or the scope is to apply them in energy harvesting and integration into flexible electronics. The focus will be on optimizing their synthesis, enhancing, as I mentioned, the piezoelectric properties through a thorough analysis of optical and structural characteristics, and ultimately proposing a novel architecture for a piezoelectric device. To answer this research question, our solution overview involves the following approach, where first we aim to choose the piezoelectric materials candidates based on the prototype device characteristics that we will try to define. Obviously, then synthesize these piezo materials through Solgian method, focusing on achieving the nanocomposites. Then we want to delve into probing the optical and structural properties of these nanocomposites to enhance the piezoelectric response. Then we want to explore the influence of nanofillers for electroactive phase, which is the step that I was kind of describing in the last part of the motivation. And the outcomes of all this research will lay the foundation for proposing a novel architecture for a piezoelectric device, which is the part of the development of, uh, of a device. Now, to gather all the information together, uh, I I can tell in our main contribution is centered on creating piezoelectric nanocomposites for flexible electronics. This involves, as I mentioned earlier, synthesizing perovskite-based materials, analyzing their optical and structural characteristics, also understanding the way nanofillers work for activating the electroactive phases, and proposing an innovative architecture for piezoelectric gadget. And last but not least, these are the stages of my dissertation. So I'm showing you here my dissertation organization, and the first stage is the review of the state of the art. Here, well, this stage is going to be brought along all the research, because we need to understand what the state of the art is, and also we understand all the concepts and that we will try to approach. But in this first stage, I just review the fundamentals of piezoelectric effects and the materials and their flexible applications. In stage number 2 is the synthesis or development of these piezoelectric materials, maybe by spin coating or for spinning processes. In stage number 3, we want to do the characterization and analysis, which is the optical and structural, to understand the optical and structural properties and to study the piezoelectric phases. Also, in which is mainly also, it's really related with stage number 4, which is the structural phase conversion by thermic processes. This is again to investigate the piezoelectric structural phases and also understand what the role of nanofillers is with our piezoelectric material, and understand them. And last but not least, the last stage, stage number 5, is the development of a device. So with all this in mind, I finish here my thesis proposal. Thanks for your attention, and here's my uh, contact information. Also, if you have any questions, feel free to ask it.
Thank you very much, Enrique. You did an excellent job explaining piezoelectricity and its application in various technological fields. In this regards, you have mentioned the technological relevance of barium titanate and lead-based materials such as PZT. However, what are the main limitations you have identified in such materials?
Well, as I was talking, maybe I can go to a slide where I mentioned PVDF and barium titanate. As I was also telling, barium titanate, PZT, they are ceramics, which means that they are brittle. So it's not that easy to have them in day-to-day applications. For example, if we would like to develop a wearable, you cannot use plain barium titanate in this kind of applications, because, as I mentioned, they are brittle. But what if we use another type of material, which is a polymer, which is PVDF, and it also has has been found to have piezoelectric properties, and to bring them together, trying to um, use both of their main characteristics, and to obtain this the the application we are looking for. So the main drawback um, is this. I mean, the part of barium titanate being brittle, and PVDF being not that much, or not that good of a piezoelectric.
Yeah, that's correct. As you said, it's important to know that ceramics are brittle due to their ionic bonds, which limits their applications. And now I'm wondering what other material exhibit piezoelectricity? You have mentioned, for example, PVDF, barium titanate, and PZT, but what other materials do you know with this property?
What other materials do I know with these kind of properties?
Yeah.
I mean, piezoelectric properties.
Piezoelectric properties.
Okay, so there is, for example, as I mentioned, from the discovery of the Curie siblings, quartz also shows it. Um, but there are also other other materials which I'm not right now. I cannot I cannot think of them. Um,
Well,
yeah.
there are many different options
Yes.
available, and we can categorize them by type. For example,
Mm.
inorganic. One of them is one of the most well-known material with piezoelectricity or piezoelectric activity is gallium arsenide. Another group is organic, and we can mention in this group to PVDF, which is a semicrystalline polymer. And also we can mention, we can talk about ceramics. As you said, we can highlight in this group the perovskite based ceramics as barium titanate. On the other hand, nanocomposites based on PVDF have gained popularity for their enhanced piezoelectric properties, specifically when combined with electroactive nanofillers. For example, carbon nanotubes or any other piezoelectric nanoparticles. Also, it is important to note that these materials are suitable for developing flexible electronics. But what are some experimental parameters that influence the piezoelectric response in these kind of materials? Could you name one or two?
Uh, so the main, can you repeat the
Parameters
question?
that influence.
Mm.
Can you mention some parameters that influence the piezoelectricity specifically in nanocomposites based on PVDF?
Well, one that I have read is temperature. One of them, the when we're trying to synthesize these materials, temperature is a crucial parameter, where it depends on the temperature you're using, then you will obtain more or less percentage of this electroactive phase. So that's an important parameter. Um, there has been also found that another parameter could be how you, also it's also related with temperature, but how, as you apply temperature to synthesize these materials, you need to also um, bring them to temperature, to environmental temperature. So there could be a process which also enhances the electroactive phases when doing this process of cooling them up, which can also which is also known as ceramic quenching. Also, another parameter which I mentioned in this discovery by Roberts by studying barium titanate is this polarization by applying an electric field. during the synthesis of this piezoelectric ceramics, and also the way we synthesize them, as I mentioned, spin coating or force spinning. That could also lead to um, um, giving way of how the faces are aligned, or we could tell, we could use better words, the domains of these materials. For example, for spinning, you're mostly obtaining uh, how to say, not tubes. I forgot the word now. Um, hilos. Well, yes. I think I can. Mm,
Yeah, sure. So basically, by producing nanofibers, we are
fibers.
allowed to align the polymeric change, which can induce the desired domains or grains with a piezoelectric response. And I agree, completely agree. And actually, I would like to mention another one, which, in my opinion, is very important. Enhancing the dispersion of the nanofiller in the polymeric matrix can affect the material's piezoelectric behavior. Therefore, we are very interested in experimental strategies aimed at achieving this goal. So basically, we can start with this issue in order to enhance the piezoelectric response, and then investigate many different processing methodologies to improve the piezoelectric response.
Yes.
And so now I would like to move to the research questions. For the optimization of the research statement and research question, I suggest the following questions. So the first one is, what is the mechanism behind the electroactivity of piezoelectric perovskites? I think that this is one of the most important questions that we can follow or to improve our research. The second one is, how does the sol gel methodology affect the structural properties of perovskites? Another one is, what are the potential applications of perovskite piezoelectric in specific energy harvesting field? So this is one of the most important for us for this research. And another one is, how can the electroactivity of perovskite piezoelectrics be optimized for practical use? I mean, with the aim of developing a prototype. And another one could be something like, what are the advantage and disadvantage of using sol gel methodology in the fabrication of perovskite piezoelectrics? So I think that I believe that answering this question, we can improve this section. What do you
Yes. Yeah, I totally agree. Um, Gathering all those questions, more specific questions, and better suited for the research, that will pave the way to obtain better results, basically. Yeah.
Yeah, exactly. And I have another question. What impact could this research potentially have on the field of piezoelectricity? Can you mention one?
An impact of in piezoelectric applications.
Yeah. Yes.
Well, first of all, the not the main one, but an important one, which is the part of using a lead-free material, which will be barium titanate in PVDF. Also, and another impact that will have is that uh, by having all these checklists. I mean, with checklists, I mean, we're using the Soldier method. We will investigate uh, how the nanofillers enhance the electroactive phases. With all these points together, we will have a material that will be able to, maybe we could have it on our skins by uh, being the last application as a wearable. Uh, so I think that's the part of an impact.
Um, um, as you mentioned, our research project is focused on exploring the characteristics of low-dimensional ferroelectric materials. To achieve this goal, we will be creating nanocomposite precursor solutions based on perovskites and then subjecting them to thermal treatments. During this process, we will closely investigate the mechanisms involved during the polymer degradation. This is an important stage during the perovskite crystallization and after for a sintering activation in order to maintain or to keep the geometry of the architecture we are attempting to achieve. By gaining a better understanding of these mechanisms, we hope to optimize the performance of piezoelectric materials. So, in this regards, we are aiming um, to gain the knowledge or the expertise in this matter, just to not to develop novel materials with piezoelectricity, but also to improve the current methodologies in order to enhance the piezoelectric behavior or many of the materials available. So I think that this is one of the most important impact that we are aiming with this research. And finally, Enrique, thank you very much for sharing the research protocol with me. While reviewing it, we have identified some areas that can be improved to enhance the quality of our research. And let's work together to make the necessary adjustments and create an outstanding protocol that meets the highest standards. So this is uh, so I think this is my final comment.
Okay, okay, thank you. I guess I will stop the recording now that we have less than
Thank you.
2 minutes. Um,